Welcome to example number 15. We have a toy car that starts from rest at the position shown and it rolls down without friction. And so it's actually technically sliding down, because if it was rolling, then we have to consider another type of energy called rolling kinetic energy. So you may want to think of this as just a little block that is sliding down this loop without friction. We're asked to determine the height h that it has to be released so that it will, when it gets to this top of this loop-de-loop, it doesn't fall off the track. So it's a great problem because it involves two things: conservation of energy and also circular motion. So there are two parts to this. We have to think of this point where it starts off initially, and then over here when the car is at this spot finally. Okay, now the distance that it starts off with is h, and when it's at the top of the loop-de-loop here, it is at a distance of 2r. r represents the radius of the loop. So let's start off with energy, because that's what we're working on. So we'll assume that the energy that it started off with initially is equal to the energy that it has at that position here, finally. The energy that it starts off with initially is made up of kinetic and potential, and the same thing finally, but we're going to cancel out some terms. We know that the initial velocity of this car is 0. So we have no kinetic energy, and we really just have potential energy, which is mgh. And then at the bottom of the loop-de-loop, well, actually not at the top of this loop-de-loop, we have two things. We have the kinetic energy it has there, 1/2 mv squared, and we also have the potential energy it has at that spot, which is mg times 2r. You'll notice that there's an m in every term. So let's go ahead and cancel out the masses here. So we have g times h is equal to 1/2 v squared plus 2gr. Not quite there yet, because we've got to get rid of the velocity. Now that's the hard part one has to realize, is now you have to connect this to what we did in the previous chapter with circular motion. When it's at this position in the loop-de-loop, there is two forces really technically acting. There is a force of gravity pulling it downwards, and there is a normal force acting downwards. And since this is moving in a circle, it is accelerating inwards towards the center, down towards the center of the circle. So now we're going to apply summing the forces along the y-axis, and we're going to assume the y-axis is going positive downwards. And this is going to create a net inward acceleration, the centripetal acceleration here, of mv squared over r is your net inward force, and then we have the normal force plus the force of gravity. And for the smallest height that we need, we want to basically at least have it just barely touching the surface. So what happens is if it goes too slow, then this normal force gets smaller and smaller and eventually becomes 0. So this term is going to be approximately 0, and so we only really have the force of gravity that is pulling it downwards towards the center. So we have mg equals mv squared over r. m's cancel out. We have the velocity squared equals r times g. So we now can substitute that into the expression above, all right, which I'll write over here. We have gh equals now 1/2, but v squared we're going to replace with r times g plus 2gr. And so that gives you, you'll notice now all the g's, by the way, cancel out. And so h equals 2.5r, which is really 5 over 2r. That's part A. Part B is saying if the car was down at the bottom here and just about to leave the track here, what would its velocity be there in terms of our radius? So I'll solve part B. Energy initially equals energy finally. Let's go from the top, where it had mgh only as potential energy. Then at the bottom, all of this potential energy is converted into kinetic energy, 1/2 mv squared. Masses cancel out, and so the velocity is equal to the root of 2 times g times h. We determined earlier in part A that the height is equal to 5 over 2r. Let's substitute that into there. We have the root of 2g times 5 over 2r. And so you'll get a velocity of now root of 5gr. Okay, and that's it for example number 15.